Good morning. This is going to be a very interesting panel. It's moderated by Steve Robinson, and it has to deal with really automation and human spaceflight. And that's going to be a subject that's going to be of great interest, considering the way the commercial industry is approaching human spaceflight with a great deal of automation. But our moderator this morning is Steve Robinson. Steve is a graduate of the University of California, Davis, receiving his bachelor's degree in mechanical engineering and aeronautics. And he co-opted with NASA starting in 1975. And after graduation, went to work for NASA and subsequently got his master's in mechanical engineering and a PhD at Stanford in mechanical engineering with a minor in aeronautics and astronautics. And he went to work for NASA in '79, working both at the Ames Research Center and the Langley Research Center. Became an astronaut in 1994 and flew 4 space shuttle flights, and also served as a backup crewman for Expedition 4 on the International Space Station. He left NASA in 2012 and became a professor at the University of California, Davis, his alma mater, and in the mechanical engineering, aerospace engineering department. So let me turn it over to Steve.
Thanks very much, Mr. Abbey. It's a real honor to be here, especially with this distinguished panel. What we're going to talk about here today is not just humans and automation, but also autonomy. And we'll talk about what we mean by that. Quick introduction to the panel: Captain Jim Wetherbee, retired U.S. Navy captain, test pilot, fighter pilot, 6-time shuttle flyer, 5 of them commander, and an expert consultant on human safety in hazardous environments. Dr. Sandra Stankovic, who is the director of the Human Performance Lab at the Harvard Medical School and Mass General Hospital, has significant experience in aerospace psychology, and is a principal investigator of several NASA research grants going on right now. Dr. Aenor Sawyer, associate professor in orthopedic surgery at the University of California, San Francisco. Over 2 decades experience in health technology innovation and remote medical management in extreme environments, including coverage of ocean rowers and Antarctic expeditioners. Her current space health work includes serving as just finished a stint as the Chief Health Innovation Officer for Trish, and is currently the director of the University of California Space Health Program. Captain Bill Shepard, I think we all know, former astronaut, former Navy SEAL, with experience and degrees in aerospace, ocean, and mechanical engineering. Very notably served as the very first commander of Expedition 1, and also happy to have here Dr. Allie Anderson. She's an assistant professor of aerospace engineering at University of Colorado Boulder. Her research is in support of humans doing exceptional work in demanding environments in 4 categories: EVA, alternative reality technologies for spaceflight applications, spaceflight-associated neuroocular syndrome, and human resilience in isolated, confined, and extreme environments. And we have Captain Dan Burbank, who former Coast Guard rescue pilot, former astronaut, former commander of the ISS, now an instructor at the Air Force Academy. And so with that, I would like to ask each of you to address your thoughts about this topic about humans in an automated and at least semi-autonomous environment. Just before we jump into that, I would like to share one slide, which is this, which is talking about what do I mean by autonomy anyway? There's lots of different definitions, and here's the one that Allie and I are using in the NASA Space Technology Research Institute, called HOME, or Habitats Optimized for Missions of Exploration. And we like this definition from Dr. Eric Frew from CU Boulder. And I'm going to go right to the second one. An autonomous system is an agent or system comprised of a machine being driven or controlled by some form of autonomy. An autonomous system always interacts with humans. So when we say autonomous, at least what I mean, is it's not that humans are entirely out of the picture. And with that, let's go to our panel, starting with Captain Wetherbee.
Well, thank you very much, Mr. Abbey, for hosting us, and Steve for moderating again. I think in the foreseeable future, we will need both automation, autonomous systems, and humans. The key is to know when to use each of these three. So first, a quick discussion of the strengths of each. So computers, of course, are fast, accurate, relentless, efficient, and they have a high capacity and bandwidth. Humans, on the other hand, have exceptionally good judgment, experience, intuition, decision-making. We can perform with incomplete information or training, and we're adaptable. And most importantly, maybe we have a fear of death, which computers do not. So when do we use the two? The computers, obviously, if we need speed, precision, efficiency, accuracy. Secondly, if we have continuous, tedious, or mundane tasks, it's good to have autonomy with some limitations. If we don't have complete information or we can't program completely and accurately, then of course we need humans. And then finally, if operations are dangerous, again with a limitation, if we cannot tolerate operation or mission failure, then we really need to have humans in the loop. Humans obviously needed when judgment is required or when incomplete information is available, when complete programming is not possible. If the capability of the automated or autonomous system is exceeded, then we need the humans. And also if the automated system or autonomous system begins to degrade or fail, then we need the humans. And then finally, as I mentioned, when operational failure or mission failure cannot be tolerated, of course, we need the humans. Quick examples, obviously, the Apollo 1 landing, where Neil had to take over and intervene. The Perseverance is a good example right now up on Mars. They desire to traverse to get to an area of interest, but that area, the place they have to traverse has rocky terrain, and so they can't do it. They're going to have to wait till later and take the long way around the rocky terrain. They also have a 3-day cycle time for planning because humans are not on site, and the humans need feedback from successive steps before they continue on to the next operation. Another current example is the Boeing Starliner, which has autonomous systems that control many of the valves with different sequencing and timers. But if a human requires to intervene, we have to think about how do we relinquish control back to the autonomous system? How do we tell the system what state they're currently in with all the different sequencing of valves? So that's a very important concept that we have to remember. Finally, I think we really need to develop, as I mentioned last year, the principles of automation and autonomous systems. And I've added a couple from last year. I'll just briefly cover the titles, but won't say much about them. First of all, the principles of autonomous operation. The system should be able to perform autonomous self-assessment of its own performance and enunciate the results of that self-assessment. That system must be self-limiting and to allow for gradual degradation if it begins to have failures. It must be able to perform self-modification with mode switching and enunciation of the new mode that it's currently in. It must be able to afford intervention by a human. And then finally, a new one is the system must be able to accept control after an intervention, as I mentioned with the example of the Boeing Starliner. Principles of human oversight also must be developed for the humans. We must expect failures and degraded performance, and remember these failures are going to be kind of weird and insidious and different than failures in conventional systems. We must be able to evaluate the performance of the automated system. We must be able to intervene and override the automated system. We must know when intervention is appropriate. We must know how to intervene. We must be able to communicate the current state of operations to the autonomous system in preparation for relinquishing control back to the system. And we must know when and how to return control to the automated system. So training is going to really increase. Some training is going to be decreased because the systems will take over some of the operation, but other training is really going to increase. We must have an increased systems knowledge, understand the failure modes, mode switching, human control, performance evaluation, override decisions, overriding control, and releasing control back to the automated system. So I think I'll stop there and turn it over to the august panel members. Thank you very much.
Thanks, Wex. And next I'll ask Dr. Stankovic to speak.
Thanks, Steve. Thanks for having me on the panel, and thank you again, Mr. Abbey, for hosting all of us today. So the goal of the lab that I work in is to promote high-level human performance in extreme operational environments. So we tend to think about automation from the perspective of promoting human systems integration. I think there's a misconception that automation is going to replace the human, but in fact, as Steve just mentioned, humans are going to remain central to the functioning of automation. It's just that their roles and the tasks that they are doing is going to change. So I think teaming rather than control is the right framework to think about here as we consider the future of automation in space. And for that, I think we really need to delineate, just as Captain Wetherbee was just saying, what things the humans are good at. What should the humans be doing in these interactions? What do the automation need to be doing? And what things can they do together? And to do that effectively, I think it really hinges on cultivating trust through very clear explainability on the part of the automation. The humans need to be able to understand what the automation is doing and why, how it came to the conclusions that it has, what it plans to do, what it actually did do, and what happened. And cultivating this kind of inter-agent understanding becomes complicated because AI systems aren't actually synthetic replications of the human brain. They don't think the way we do. They don't assess risk. They don't make conclusions like humans. They use binning and patterns and take actions based on previous actions. And so following their thought process through something like a code is just extremely difficult for a human to understand. So I think one of the biggest challenges that we're facing now is of information presentation. How does the automation communicate what it's intending to do, its reasoning effectively to the human? What are the right channels and modalities for that kind of communication? If you look at human-human teaming, we don't just communicate through language. We have gestures. We have all kinds of other modalities that we use. What is the right kind of bandwidth for that information? And how can that presentation change and adapt and be customized for the humans to configure based on their needs and in response to dynamic and changing situations? I think the declutter button on the shuttle is a great example of this, of an interface that presents different levels of information density that humans can control based on what suits their needs in a specific context. And that will, of course, vary with proficiency and experience level and situational factors like workload and task criticality. But ultimately, I think the crew needs to have a very central role in defining how these interfaces are customized and tailoring that value to nuisance ratio. So those are just some of the open-ended questions that I'm most excited about, and I'm looking forward to hearing the thoughts of the other panelists. Thanks.
Thank you very much, Sandra. And I appreciate everybody being pretty brief in their remarks so we can get some good questions from the audience after we go through the cycle. All right, Dr. Sawyer, you're next on my list.
Thank you, Steve, and thank you, Mr. Abbey. This is a really great honor to be on this panel and in this meeting. I've certainly learned much from it each time I've gone and attended. So, Steve, thank you. I'd like to talk a little bit about what we're really passionate about in our lab and the work that I think could be beneficial to improving crew health and safety and also mission planning. And that is a paradigm shift beyond the tethered telemedicine models more to an augmented to autonomous self-health and medical management system. This is going to be not just technological shifts, but cultural shifts as well to advance this model, that it'll move from a reactive to a proactive type strategy so we can go upstream with awareness, or what we call health sense, especially in key asymptomatic but abnormal states that already decrease performance, but predispose to clinical scenarios if not picked up on early. Some simple ones to think about are hydration, which is actually thirst is our first indicator, but it's a late sign. So we don't have gauges for things like hydration that are really reliable for us and allow us to make early corrections. Same thing with energy balance, fatigue, and manage stress. So those are upstream problems that are linked to multiple medical concerns in spaceflight. And if we can catch them early with an integrated suite of sensing capabilities, advanced computational with edge analytics and actionable insights, and a delivery of the information in an audience-specific way, we'll have a much better way to have an efficient and effective healthcare system that is untethered from Earth. And it's the same type of models we're trying to build in terrestrial healthcare in creating more distributed but not diluted healthcare. The idea of health sense also is creating a health sense matrix that would really be the information engine under a precision health model. So we start looking at the human as on a continuum from wellness to illness and back again, rather than dividing up healthy or unhealthy. And it's the way we do healthcare right now, unfortunately, but we need to break down the silos between health and wellness. We all move from wellness to illness and hopefully back again continuously. And we see these dynamic shifts in spaceflight as well. What we don't have is a really good in-flight and dynamic understanding of all those changes, and particularly at an individual level. The other thing we don't have is the ability to contextualize the human-generated data in the context of the environment. And I think you heard Dorit talk about that earlier, and also in the context of their holomic, or all the other capacities that we have to measure the risk predictive capabilities of that. So we need to do more detailed information about individuals. But the main thing is, I think you need to make sure that you're giving value back to the people that are at the center of the measuring system, which would be the crew. And this is what it was really fun to hear Sandra say, the value to nuisance ratio. And we came up with this idea because of trying to leverage remote care models, hospital in the home, putting sensors in people's homes, health apps, et cetera. And we found if they didn't get more value than nuisance, then that we were done. So we call it the value to nuisance ratio. And if it's greater than one, you've won. If it's less than one, you're done. So it's really, really important that we're providing minimally intrusive or non-intrusive capabilities to sense human-generated data and environmental data, and then give actionable, valuable information back, defined by the individual, actually, or we won't have much uptake in this, and it'll look like we're layering on more and more measurement that brings more concerns to the crew. If we can master that piece, the rest of it, I think technologically we can master, but we've got to pay attention to that cultural piece.
All right, thank you, Aenor. Great perspective. And now we'll go to Captain Shepard.
Hey, Steve and George, thanks again for doing this. I think this is one of the more interesting panels. I've got maybe two big points to make. One is that I still don't think the industry, defense and aerospace, has an adequate, if you will, architecture or coordinate system to map how the functions of these complex systems interrelate and how they translate into the functional and physical elements of hardware and software in a big program. We struggled with this early on in the NASA programs that I worked on, and we generally write a work breakdown structure. And that is what's used to have the contractors build things. But it's essentially what piece connects to what piece. And the functions are kind of floating around in this sea of verbiage. We do not have a way to architect how this is done. So how can we delineate what the computer should do and what the humans should do and what they should do together? To me, this is the root of the problem. If we had a reasonable architecture that was useful, that tend to cover all the bases, I think we'd be way ahead of the game. Then we could say, look, a board is something that both sides of this equation should be able to command, but maybe a configuration for engine start is something a computer should do, as Jim pointed out. That's one thing. I don't feel we have an adequate understanding of what we want for performance of components, subsystems, and systems. We talk about different levels of redundancy based on the reliability of various components and things. But is a system really tough? Is it robust? And how do we quantify that? NASA's rule of thumb has been we need 3 ways to do everything. I don't think that's the best way to build hardware and software in the future. We've got to do it more intelligently. And I cite the Russian model for having a primary system that's very elaborate, but lots of mechanical backups. I think that's an extremely good culture. On to computers. I think we have to recognize that computers are different animals. In my thinking, we have millions of transistors on a small chip. And so we've compressed space, and we take tens of thousands of hours of programming, and the computer can run that in a couple of microseconds or milliseconds. So this machine is compressing space and time. However, it still is quite capable of doing the wrong thing. And I will throw out some instances. Software routines that divide by zero, solder balls flying around and hitting switches, keystrokes that bounce, various latency or bad data that shows up on indications. And over again in my time at Houston, I've seen people who have essentially faith in numbers. They look at a display, and to them that is truth. But the more seasoned people, particularly in the astronaut office, John Young in particular, would often take the position that computers can lie to you, and we should never forget that. So this is another aspect of how we move into this deeper level of autonomous systems and automation that we really ought to be careful with. That's all I got.
All right, thank you, Ship. Dr. Anderson, you're next.
Thank you very much, Steve, and thank you, Mr. Abbey. It's really exciting to be on this panel, and I'm particularly fascinated by all the comments that my colleagues have made, and I'm just grateful to also be able to provide a little bit of my own opinions on this same topic. So when I think about the utility of autonomy for human spaceflight, to me, the greatest priorities for where we really need to develop and certify our capabilities are really in mission critical areas. I think that oftentimes we focus on the broad spectrum of ways in which autonomy could be integrated into missions. But I think that, you know, there's a saying that, you know, the best way to reduce the technology readiness level of anything is to send it to space. And I think that that's also true for autonomy. So in particular, embodied robots are, you know, now in multiple dimensions, and it's difficult to use those kinds of systems in ways that are predictable to humans and able to predict the behaviors of humans. And then similarly for algorithmic autonomy, thinking about how so many of those methods rely upon a vast amount of data in order to be accurate and certifiable, and just our limited ability to gain the data that we need for those kinds of systems. So when I think about some of the priorities that are critical, you know, I'll use the same sort of philosophy that Aenor was talking about, but focused on the health and safety of the spacecraft system itself in conjunction with the humans. So I think that focusing on safety is sort of the analogous to focusing on preventing injury. So the ability to use autonomous systems to focus on fault detection and emergency response, where those mission critical tasks may not be directly observable, and especially on timescales that humans are able to react in the same way. I think also similarly the idea of wellness, so the analogous to maintenance and repair, is another important area where we really need to build out and focus on developing technology capabilities. One of the challenges with using AI for repair and maintenance is that by not having the crew member directly involved in those activities, you run the risk of also reducing situation awareness. And so I think that that relates to some of the comments that Sandra was making as well. And then I think, especially for long duration exploration missions, one of the areas that I'm most excited about thinking about is for novel scenarios that we haven't yet encountered and for decision making. And so a lot of autonomy development areas are so focused, again, like I said, on prior data that has been collected, that as we move to, say, a mission to Mars, the idea of certifying that software, the idea of encountering novel failure modes, when you think about how crew members developed expertise in understanding how ISS components fail just due to their experience, intuition, their ability to sense and to identify these novel situations that hadn't yet been encountered. I think this emphasizes the need for online learning approaches and for the autonomous systems to take and incorporate information from humans and learning from humans as a way to eventually become independent of humans, maybe not independent, but to essentially to take on more capabilities as missions go on. And then I think the last thing I want to emphasize is that one of the greatest challenges in incorporating, so I've talked a lot about the technology challenges for incorporating autonomy into future human spaceflight missions, but I think one of the most critical areas that we really need to focus on is the human's interpretation and ability to interact with those systems. And in particular, trust, as Sandra also mentioned, is a critical area. And when we talk about trust, we really try to focus on well-calibrated trust, so you reduce the potential for over-reliance as well as underutilization of those systems. And I think that I'll echo again what Captain Wetherbee had said, which is that, you know, understanding how that human and the autonomous system interact and their relative levels of capabilities and how do we assign decision authority in those environments, I think is still an open area of investigation. So thank you very much.
Thank you, Ellie. Fits in perfectly. And Captain Burbank, over to you, Dana.
Okay, Steve, thanks. Mr. Abbey and Steve, Dr. Sutton, Rice, Baker Institute, thank you all for letting us participate in this. I think this is as the other panelists have said, I think this is an incredibly important panel, and it's incredibly relevant to all the things we consider doing in space. And it's probably one of the biggest challenges we have. And I guess as I think about it from an operator's perspective, it seems to me that the complexity of the spacecraft has exponentially increased. And it's gotten to the point where, you know, if you look back to the early days of the space program, be it the Russians or be it the Mercury, Gemini, and Apollo phases, the crew members flew the vehicle. So there was a tremendous amount of situational awareness on the part of the crew. There was a very tight feedback loop and the human in the loop kind of operations of those. The vehicles were certainly at the limit of what engineering could do at those stages, but they required a human operator, and the human operator was deeply embedded, at least in all the dynamic phases of flight. And for the shuttle, I think that was also true, with the exception of the very beginning of ascent. The vehicle was largely able to fly itself for the dynamic phases, but I guess one exception to that would be like the rendezvous, for example. So you had an entire crew all tightly integrated, very, very aware, very practiced in how to execute a very critical operation. Very training heavy, task based. Good book by James Reason on human error, and certainly lots of other papers and things in the literature about this. But very task based, and the shuttle with its complexity, 800 or so switches, 400 circuit breakers, very, very obscure often indications to the crew that would drive a boldface, critical response, without hesitation on the part of the crew to take action to correct an anomaly, at least in some of the dynamic phases. So going through a couple of shuttle training flows, not as a pilot or commander, but as a MS2, for example, my last one, I felt like I had a lot of situational awareness. I'd spent enough time in the sim. The vehicle, you could almost close your eyes and imagine where those switches were on the overhead that you might be called upon to act. The otherwise obscure messages to the uninitiated would have this new meaning that you would understand. It was a very different world, I found, when it came to actually being on board space station, million-pound mass, 400,000 kilograms, and a level of complexity that far exceeded even the shuttle, I think. Whereas the crew flew the vehicles in the early days, even to include the shuttle, I would say the ground flies the space station. The typicals, and my information on this is 10 years out of date already, hard to believe. But if you think, if I think through what my awareness was on a day-to-day basis and the configuration of the space station systems, it was fairly limited. In truth, there was not a lot of dynamic critical events that would require immediate response, boldface kinds of things. We would have a leak, a fire, a depress, ammonia leak, those kinds of things. Maybe a loss of comm where you'd have to step in. But for most of those things, there was time to think. So we trained crews with a skills-based methodology where you gave them the basic information, taught them how to deal with a couple of boldface kinds of critical procedures, but generally speaking, the ground's going to fly the vehicle and do it very, very well. Your day-to-day awareness of the systems on the vehicle really was what came up in the daily summary, the morning mail. And you might not even be able to tease out what the specifics were of the vehicle health by looking at one of the PCS displays, the computer, the laptop that would give you, awareness of what was being enunciated as something that was in an alert state or a caution state. And often those messages would be inhibited or they'd be suppressed, and somebody on the ground was managing all of that. To me, I think there's a very, very big gap as you contemplate, flying deeper into the cislunar space and then deep space missions, where the vehicle has got to fly the vehicle because of the comm latency, because of the lack of abort options. There's a certain set of roles the crew has evolved to from the early days of space to the International Space Station operations, and we've become scientists and co-investigators and lab, and test subjects, and we've become maintainers, something we'd never done before either. But we've essentially ceded the role of having to jump in and take and literally fly the vehicle. So we have to assume the vehicles are going to have that same level of complexity as the ISS, but the vehicle needs to, as all the other panelists have alluded to in various ways, the vehicle's got to be self-aware, it's got to be self-restorative, and most importantly, I think the biggest challenges are in the transition for when the computer is not able to fly the vehicle, when a system failure becomes so critical that the human has to intervene. And that's where it really becomes critical, as been mentioned, that there's enough situational awareness, that there's been enough decluttering and accentuation of the critical information to do a crisp handover to the human being. And ideally, that would happen in a blended fashion where the awareness, where the computer, as it was degrading or gradually handing over the operation, the human was being brought into the loop and fed the information they need. I think that's one of the most challenging areas, and it's something that with commercial crew right now, with some of the vehicles, that's not a mode necessarily that's being contemplated, the shared control, the shared authority between the two. So I think this is very timely, and I'm very anxious to hear what we have for questions and hear what the panelists and others would like to add to that. Thanks, Steve.
Thanks, Dan. I'll just make one little wrap-up statement here. The Home Institute that I mentioned before, that Allie is a major player on, but it's about 75 researchers working for NASA, thinking about autonomous, semi-autonomous deep space habitats that are intermittently crewed, which is something we really haven't done before, maybe a little bit on Skylab. And we've all mentioned here, I think in the panel so far, the importance of a vehicle that is guided mostly by automatic and autonomous software, the importance of humans either on the ground or in the spacecraft itself actually having awareness of what's going on, awareness supplemented by trust to form a real partnership. And what that's going to take, in my opinion, is the ability for the vehicle to know enough about itself, to be self-aware enough, to be able to predict the short-term state, to allow the humans not to instantly gain knowledge of its state, but to have an idea of where it's going. And that is, I think, a very important part that we don't have now. Mission Control has that. Mission Control does that. Now we have to have it on board. So is that a digital twin? Is that some sort of autonomy human teaming? The answer is yes and yes. So that's a big topic that quite a few people are working on right now. Okay, with that, how much time do we have? Baker Institute, can you tell
21
us?
minutes, I think.
I think you have as much as you need.
Nobody's ever told me that before. That's awesome. How much?
I think we
I
go
won't
to
ask
a
it.
quarter.
I won't push this any further. So I do want to open it up. We have in the Q&A from David Aleksandra, kind of a big open question with respect to autonomy and human ops. How do we prepare for the transition that we've mentioned a couple times to a mixed operation modality for Moon and Mars? So what he is talking about is the uncrewed station or habitat transitioning to a crewed system rather than permanently crewed. So this is the intermittently crewed spacecraft, and how do we do those transitions? Who wants to jump into that?
Well, this might not be directly on target, but it goes there. So I think I'm really struck by how, when I got more into space medicine, how I realized how unmonitored the human is compared to the rest of the spacecraft. It's the least monitored component of the whole system, but it's a critical component and it's a vulnerable component. And in some ways, if we could link the monitoring of the human to the monitoring of the system and create more closed feedback processes that involved the human's response to the system, it would be highly informative and help go upstream on system problems. Perhaps some of the degradation we're seeing in the human physiologically is related to CO2 or some other parameter in the environment. So getting an earlier signal about that, I'm really interested in figuring out how we can create more in-mission information about the human that's used in mission rather than just sent down to mission control, but have it tightly linked as a component of the actual spacecraft system. It seems the human's been left out of the equation a bit.
Well, Wex, what do you think about the human being monitored more, kind of like the spacecraft it is itself?
So let me start by saying, if I understood the question, the very things that we're talking about can help us to get to a place where we transition to having both autonomous and human control as we venture out further. I think what we're pleading for industry to do is to create an overarching framework which starts with a vision of where we want to go, what's the mission, what are the principles of automation and human intervention, things like that I talked about. But then critically important, what Shep talked about, Captain Shepard, we need to map how the pieces and the functions work together, develop an architecture so it's very clear how everything works together, and then define and decide the performance of the different components, reliability, et cetera. From that overarching framework, then you can develop the training and testing protocols and everything to train the crew to design the system so that they have a chance of succeeding as we venture out further. So the very thing that we're talking about now, we need to develop it further to be able to venture deeper into space.
Allie, did you want to talk about, or let's go Shep then Allie. Okay, go ahead.
Yeah, Mike Lembeck had a real good question about exactly what Jim was talking about. And he and I were chatting about it. One of the things about doing this, this architecture, the stuff that you're dealing with is not orthogonal, which engineers and mathematicians really like, but it's not. You're dealing with things that are very coupled and interrelated, and they change with the context of what's going on in the mission. And that's why creating this map, or this relationship, or this network, whatever you want to call it, is so difficult. But I think we ought to recognize that it's difficult and figure out how to solve it.
The other thing that I forgot to mention, Shep brought it up the other day, in the principles, we need to develop some kind of ethics, because computers and autonomous systems are going to be making decisions, and it is going to require an ethical framework. Because human lives are at stake.
Right, which speaks to the issue of trust that I think Sandra and Allie brought up. Allie?
Yeah, I wanted to add on one thing to what Dr. Sawyer said, which I agree with, that the idea, so one of the things that we're working on is building models from monitoring human responses to autonomy in order to predict trust, workload, and situation simultaneously. And I think one of the embedded questions maybe that Steve alluded to was that, how acceptable would it be to monitor the physiological responses and use that as a modeled algorithm within the autonomy to predict what the human's situation awareness was, or workload was. And I think that physiological approaches can definitely inform whether or not someone is transitioning to the vehicle with the level of awareness that we would like them to. But there's other information that we can also observe that's not necessarily associated with physiological monitoring that can augment that, such as observable information like, did the human request more information from the autonomy before making a decision, things like that. And I think the other flip side of that coin is also providing additional display information and opportunities to dig deeper to ensure that that handoff, that transition to an uninhabited vehicle where there isn't a crew member doing that handoff, but rather the autonomy is doing that handoff, such that the human has the opportunity to gain additional insight through directly querying and probing, say, to understand whether or not it trusts the sensors that are providing feedback, getting to the point of sometimes computers can lie to you. Well, providing multiple opportunities for the human to dig into what the computer is saying to them is another great way to act as a countermeasure to some of those challenges.
Well, let me ask Sandra then, if we're going to monitor the humans to build up a better state estimation of the entire system. So we've got humans, we've got software, and we've got hardware, all driven by sensors. What do we do about the fact that maybe the humans don't want to be monitored? Maybe the humans are worried about other people surveilling them and gathering information that have a negative connotation. How do we deal with that? It's almost a cultural thing.
It absolutely is. That's a great question, Steve. And I don't know if there's a clear answer to that. I mean, I think part of it depends on really defining what mission critical and safety critical information is when it comes to looking at human data. But measuring humans is really challenging. So even having an idea of what the right measures that you want is, it's still going to be very difficult to come up with the best set of sensors and really isolate the signatures that you want. I'm really curious to see what some of the other panelists think about that too.
Well, Aenor, so what do we do? Do we monitor the humans just as little as we can get away with and still have that trust and situational awareness, or do we monitor as much as we possibly can?
I'm actually a fan of needs driven, so use case driven. So starting out with the so what factor, like why are you monitoring? And that gets you down select to certain sensors for the human, certain ones for the environment that are going to give you that information. And fortunately, we can only express ourselves physiologically in so many ways. So there are a core set of parameters that we're going to use over and over for different use cases with different algorithms and different weighting of the variables. But I think the main thing is there has to be a reason you're doing it, and it has to matter to the wearer, of course, as number one, and then to the other stakeholders in the way that they need it. But it also has to matter to the mission. So, for instance, understanding if the human's even ready to take over. What's their readiness capability? And there are some an example is a company I have no alliance, but Fatigue Science, where they're doing risk prediction, and they can tell you when someone's going to actually crash energy-wise 2 weeks out. You could say that is not the ideal person to plan for the EVA or whatever, or you take actions to change that course so that you can give them information about sleep, hydration, and fuel sources. So they change the direction that the trajectory they're predicted to crump in a week. So I think you would also give information back to the system when is the human not ready to take over. So that would feed into the whole integration of that human and system interface and handoff. But it's got to matter that we can't measure just for the sake of measuring. That's my same thing in healthcare. It seems it hasn't gotten us anywhere.
Great perspective. And another thing that Dr. Warren brings up on the chat is that perhaps you could keep this data on board without shipping it down to.
That's the point. Yeah.
Yeah.
And I think, Steve, you mentioned this too, even when you could give the example yourself of, we want the astronauts to have the information that they can act on so they get the right information at the right time to make the right choice for themselves, but not just the individual, but the commander needs it. You mentioned this about the EVA suit when mission control knew something before you did.
Yeah, traditionally the flight medicine folks in mission control know your metabolic rate when you're doing an EVA, but you don't. And so we're experimenting now with some head-mounted or helmet-mounted displays to think about providing that information for astronauts in the future, and maybe in the near future in the NBL training. Dan?
Yeah, so I was going to basically acknowledge what Liz was saying, and that if you keep the information on board, that's probably a good thing. I guess from a crew perspective, there's always, in general, maybe this is just in the human nature, reluctance to want to have to share a lot of information, reluctance to have ongoing surveillance. Now, with that said, thinking about it from the overall mission success standpoint, I found it surprising how sometimes fatigue would crop, chronic fatigue would crop up on you on orbit, and you might not recognize it, but you'd recognize it in your crew members. And you might not even be able to test it in one of the cognitive tests that we use, or the reaction time tests. These would be, you would just see somebody is tired just by looking at their eyes and so forth. So I think the fact that, if you just leave it up just to the humans to monitor the humans, then the means through which you're monitoring yourself is suspect. It's compromised potentially. So, but I think it is a really, really tough space. And I think there would always be concern, but just the way we manage medical information and whether it's a mission impact or not, and, in the compartmentalization of that kind of information that gets to the surgeon console, and only a very, very skinny down version of it makes its way even to the flight director. So I think we've honored those kinds of considerations well in the past, and I think all that's pretty good. And it's good when you have a large crew and a lot of bandwidth and a lot of bench depth on the crew, and you've got the proximity to Earth and aboard capabilities in a big vehicle with lots and lots of volume. So maybe a little bit different story when we're talking about deep space.
Thanks, Dan. Shep, did you have your hand up, or is that a?
Yeah, I just wanted to say that I think the way to do this is to have the crew convinced that the use of this data is going to improve their performance. And if you do that, then it will be accepted. If it's used for other means, I think you're going to get pushback. And one of my unfulfilled career fantasies was to be a carrier pilot like Captain Wetherbee and land. Jim, was it like 124 landings at night on the carrier or something like that? At any rate, he and I often exchange notes about video that I watch of Navy pilots trying to land on the carrier and how they manipulate the throttle and the stick. And I think you can learn something by their technique, but this is probably something that they learned by doing it over and over again. But, if there was positive feedback that, this kind of control input is good, this control input is bad, I think these types of tasks could be acquired, the skill for them could be acquired much more rapidly.
So this all brings us to and by the way, Shep, I'm really sorry about your disappointing career, but Chuck Oman, everybody's friend from MIT's Human Systems Lab, asks, will new human roles in managing complex automation on multi-year missions require new approaches to onboard training and recency maintenance? The answer is certainly yes, but it's a great leading question. And I think I want to ask Allie about that, because Allie is and the reason I'm doing this, putting you on the spot, is within this home institute, we have 5 research thrusts. And Allie is the leader of the thrust that's called Human Automation Teaming. Right down her alley.
Steve keeps mentioning it, but what he has not mentioned yet is that he's the director of the entire institute. So, but also I know that Sandra also has her hand up, so I'll try and be brief. So I agree with Steve's comment that the short answer is yes. I think that one of the big challenges on that front is that especially if we engage with some of the online learning approaches, that the training associated with working with these autonomous systems is one thing, but that also there is an opportunity for perpetual interaction in order to pursue the ability to increase the automation's capabilities as we go forward. In terms of the overarching objectives so I think a good example for one area where this might be critical would be something like landing, where you have super high fidelity training on the ground, and then you're transitioning for period of time, we'll just use Mars as an example, to then where you're going through that landing process. And so that would be an opportunity where the autonomous systems you're engaging with are not things that are in that sort of core functionality of maintenance, safety, and repair during the transit period. And so I know that there's a lot of work being done to try to develop alternative or novel training environments for those periods in order to ensure recency. And one of the things we're working on is immersive technologies such as virtual reality as a way, and I know that NASA's, one of the world leaders in developing training in virtual reality, but trying to think about how we could increase transitions in automation during that training process and kind of mimicking the autonomous systems capability while in those virtualized training environments in order to prepare for that landing and recency. So again, I know Sandra has her hand up, so I'll hand off to her.
Yeah, and just to mention something else that Dan said, when we're talking about onboard training or just-in-time training, sometimes we do distinguish between skills-based and task-based training. Sandra?
Thanks, Stephen. Thanks, Allie. Thanks, Allie, for those comments. And Chuck, great question. Thank you for that. I wanted to pick up on a thread that Allie had mentioned in her opening comments about novel failure modes. I think that was a great point. Thanks for bringing that up, Allie. We're so good now at these scripted, really well choreographed operations that we've gotten a lot of experience doing in low Earth orbit. But when we look ahead to more asynchronous, more Earth independent operations, it's impossible to predict all of the different failures that will be cropping up. So I think teaching crews how to dynamically problem solve is going to be a huge area that we need more research into, and coming up with strategies for problem solving in collaboration with automation. And a lot of that, I think, will depend on some of these things we've already mentioned about information density. What is the right information? Who has the information? Who needs the information? Is it information from the human? Is it information from the system? So I think coming up with new approaches to training that more improvisational thinking will be really critical.
It occurs to me when you bring up novel problems. I mean, the whole reason we go to space is to put ourselves in novel situations and learn from them. That is the driver, and they won't all be desirable situations, as all of us who've been in space found that out. Shep, and then Aenor.
I just want to say that I spend a lot of time looking at some of the online on-demand resources, particularly all the open courseware and things like YouTube. And I think this is the paradigm for how at least the maintenance of skills should be done up on orbit. So I think having canned resources that the astronauts can dredge up as they need to or as they have interest in on orbit is going to be a big part of the training component.
That's something that Dan and I both tried with significant success. Is we cooked up this plan where we would make training videos of ourselves at the peak of our training, teaching ourselves a year later in space when we'd probably forgotten a lot of that stuff. And you could take, we found that you could take several hours of training, compress it into about 2 minutes of video of Steve talking to Steve. And I used it. And it worked great. It was like, oh yeah, so yes, that definitely works as a just-in-time training approach, at least for some people. Dana, you want to follow up on that, and then we'll go over to Aenor?
Yeah, just do one quick follow-up. And Steve, I did the same thing. In fact, for Expedition 2930, 29 was supposed to have a 2-month handover with the Expedition 2829 crew, Fossum and Satoshi Furukawa and Sergei Volkov. But because of a Progress rocket failure, our handover got shrunk down to less than a week. And so we ended up doing all virtual, we basically, Mike Fossum and his crew downlinked, oh my gosh, must have been at least 50 or 60 separate little videos that basically incorporated all here's how you fly this tall ship in space. All the things you would learn by seeing for the 2 months of overlap into something that I could study ahead of time, our entire crew could study ahead of time, and then we could get up there and in 4 days hand over command, and I'd be reasonably okay to manage that. So very, very successful. It's work. We've had to do it.
Human to human training. Eventually, we're going to have software to human training, because when the vehicle's up there for 2 years with no people on it, it's going to be learning. Learning software is critical to an autonomous spacecraft. And so when the human arrives, it must have already learned from the onboard software before launch what the state is and what transitions there are and what sort of degradations they have to worry about. Aenor.
That's exactly the subject I was going to go to. So it's spooky, but thanks, Steve. But, we've talked a lot about what data is important. And so we have a phrase in our lab called metadata. Instead of metadata or megadata, it's metadata, what matters. And we're not going to know that all up front. We're going to make, evidence-based and our best guesses. But we've got to have a way to then sort out, as we're using the information, what we didn't use, so that we can start, sifting away the data we don't need. So that's a learning system. And the whole spacecraft system, but also the human system, has got to be a learning and adaptive system, which is really critical and also really scary, because there are possibilities now, as we talk about advanced computational capabilities, AI, ML, neural networks, where with AI in particular, it's a decision-making process. And when it starts making decisions about its decisions, there are risks, there are unintended consequences that I think we also need to map out, not to obstruct, but to set the fears out there and allay them or put in some protections. There's a great book, Human Compatible, by Stuart Russell at UC Berkeley, that talks about that, the unintended consequences of the ever increasing capability of AI in learning and adapting. So I wanted to throw that in.
A pretty active area of robotic research these days, it's certainly relevant for internal robotics and spacecraft, is robotics learning from humans. So you have a pretty capable robot, but it actually doesn't know how to do the thing you want it to do. And so in what way shall you demonstrate or guide it through? And that guiding doesn't have to happen in space. It could happen on the ground. And then you could ship up the new just-in-time training lesson for the robot itself to then more effectively team with a human. I'm going to jump over to a statement from Dr. Dunbar, Bonnie Dunbar, our friend, which has to do with monitoring, health monitoring of astronauts. And here was a case where her research team proposed integrating crew-worn sensors into the Smart Habitat environmental control and life support system so that you could actually detect if the humans were responding to higher CO2 levels in a negative way. And it was turned down. Proposal was turned down, partially with a statement that the addition of crew-worn sensors to inform the smart system while the crew was present is tangential to the solicitation. And Bonnie summarizes by saying software developed for an uninhabited smart app will need to recognize when the crew is present and not try to correct the human anomaly, which is another science fiction movie in itself, I think. Great comments, Bonnie. How are we doing on time, Mr. Abbey?
I think you have a little more time, another 10 minutes or so.
Okay. Well, we'll definitely take it. So I want to bring something up, everybody. We've been talking about just-in-time training. We've been talking about trust of the human in their surrounding autonomous and learning systems. We've been talking about AI explaining what it's doing and what it wants to do to humans, which is a very difficult thing to do because AI doesn't think at all. In fact, many kinds of machine learning doesn't even follow a logical process. It's more of a stochastic pattern recognition and binning or classification. So here's what I want to bring up. Should astronauts of the future be different in the sense that they have to know about how machine learning actually works? Do they need to be able to understand code at a deeper level than most of us ever did? Is that an important prerequisite for future astronauts, either through training or selection? Let's ask somebody who's gone through that experience recently, Aleksandra.
Thanks, Steve. Yeah, I mean, that I think is a panel of its own. What are the right skills for future spaceflight? Identifying, which competencies match to which kind of skills. It relies on a clear understanding of future ConOps that I'm not sure we really have just yet, particularly as we're thinking about these kind of novel opportunities that interaction with robotics and automation will enable. So I'm really curious to see how that evolves. But I will just say, kind of on a personal level, I don't really understand how my iPhone works on a deep technical level, but that doesn't really prevent me from using it effectively. So I think there's a difference between understanding the kind of the programmatics behind the equipment that you're using and being able to understand their functionality and coming to rely upon, what it will do in a given context, that kind of predictability in the automation that comes from more interaction with technologies.
We've all been in that situation where we're interacting with some piece of high technology, and we find ourselves wondering, do I not just understand this, or is it actually malfunctioning? But we have that problem with people too sometimes, don't we? Shep and then Wex, and then Aenor.
I think we should attack the problem from a different dimension, actually. Ever since we started having computing machines, we've had very arcane languages, and we've had humans adapt to the language to talk to the machine. We need to go the other way. We need to figure out how we can adapt the talking of to the machine to the human. And I don't think learning Python is the answer.
I think all of my students, all of our students, for all of us in academia, would probably agree with that until they learn Python. Wex, then Aenor.
Yeah, I was just going to say the quick answer is yes. If I'm working in a dangerous environment with a system, I'm going to want to know everything about that system. And I appreciate what Shep says and agree with it. However we decide to do it, I'll play the game with your football and your rules on your field, and I'll still learn how to survive and win the game.
Aenor.
Yeah, hard to top that. I was thinking also one thing we struggle with in healthcare is the more we tech enable, are we taking away skills? And so what's the capability? How do we maintain a capability for when the high tech capacity suddenly goes out? And how do we maintain our low tech capacities, our ingenuity, that type of thing? That's a question beyond me. And I think some people here have probably thought a lot about it, but that is one thing we're really concerned about in the ER. You'd like to have someone, if you roll in on a gurney with a heart attack, you'd like them to have memorized the algorithm, not be searching for it and scrolling through the glass screen. So I just wanted to say, how do we keep a balance of maintaining skills while we're actually replacing skills?
And as our test pilots in the crowd know, recency is something that takes constant practice. Same thing with being a musician. Same thing with being a physician, or an athlete. But we're pretty poor at, I think many of us are pretty poor at self-assessing. And so having quantitative ways of assessing our readiness to do something, whether it's takeover or repair or, EVA tasks or something like that, are probably more important in an autonomous vehicle that has briefly visiting humans. Let's see. I wanted to hear, Ellie, you're an educator, and with deep experience in the world of spaceflight research, with aspirations of flying in space yourself. What kind of selection should we be thinking about for future astronauts here?
So I wanted to comment on this. So as someone who's currently teaching a computational methods class to 320 sophomores who hate computer programming, I feel like if I told them that would help them become astronauts, then they might actually like my class more. So I'm in favor of this in theory. No, but I think it's funny. I was actually maybe going to take a little bit of the counter. So I wouldn't go so far as to say that the degree to which it should influence selection. It's well beyond anything I can comment on. But I think that there's actually something very important about having technical competency for understanding computer programming, because I think, especially for long duration exploration missions where maybe the ability to send massive software updates might be limited by bandwidth, or the ability to need to troubleshoot something in an emergency situation, to be able to read and understand code and understand really kind of where some of these decisions are coming from. To me, it still gets back at how and the mechanical analogy would be, you wouldn't want to send someone who is unable to fix a piece of hardware mechanically. And if we're going to start relying a lot more on computational means, the ability to fix and adjust and to have a well-calibrated sense of the system's capabilities. I think that actually understanding the maybe not necessarily needing to code the algorithm, but to understand the capabilities of the algorithm and the limitations of the algorithm in order to understand its reliability when it's telling you something. I think that that's actually a really important skill. And, to get at Captain Weatherbee's comment, whether or not that is I would imagine anyone who was putting their life on the line with a system like that would take the time to learn those rules and play that football game. So.
Yeah, I would agree, especially when you learn something in a hazardous environment. One of the main reasons you're learning it is to recognize it when things start going wrong before they have gone critically wrong. So one thing we think a lot about for a spacecraft that's going to last 15 years and only have people there every couple of years. How do we understand degradation? What does degradation mean, especially in components that don't have a lot of life before they launched? So we don't have that big statistical library of reliability for these components. We've all flown in space with, serial number 1 of something, and when it breaks, even the designers say, "Whoa, look at that!" So trying to understand how things degrade in space, including all the critical components, so software, so hardware, so peopleware, can all have these degradation aspects in space. And I think up until recently, I thought a lot more about failures, and now I'm thinking about pre-failure, thinking about how do we take the data we know and model forward to understand, just like Aenor was saying about people, to understand what could happen in a week or less, and take corrective action before it becomes critical. Shep, go ahead.
I think that could be one of the real benefits of AI, to do stuff like that, because it can poke into a lot of corners that humans don't have the insight or the time to deal with. So one of the bigger technical challenges right now I see is in making really, really small electronic components that'll survive in space, because the background radiation tends to screw things up. But maybe there's a way that AI could be really smart and say, this gate in the chip or this part of the memory bank is having a bad day, and we're not going to listen to him anymore. We're going to move what he does over somewhere else. That would be an extremely useful capability if we could make it work.
Agree. And actually, lots of people agree. I think that you've hit the nail right on the head. I think we won't have these kind of spacecraft without that kind of capability. Sandra.
Thanks. I just wanted to take the opportunity and echo what Aenor mentioned earlier about de-skillment. I think that kind of consideration of failure possibilities in hardware and degradation, it brings a lot of focus back on making sure that we build a robustness, a kind of an elasticity into our operations, that we know how to use the automation if it's available, but should the automation fail, that we're also maintaining that skill and competency level in the crew so that we can continue to operate safely without it.
And Dan?
Yeah, and maybe just one other thought, with the discussion of autonomy and automation and graceful degradation and an intuitive handover of control authority, those kinds of things. And maybe this also speaks to some of the comments I think that you guys had when you had your pre-chat discussion. Shep, you talked about designing for robustness, overall, like system robustness via, redundancy, and what's the right level of redundancy. And is there some elegance in having the redundancy be dissimilar and very basic, like in an H60, being able to turn the aux hydraulics off and be able to just manually fly it and take a number of possible failures out of the equation, at least be able to fly it BFS on the shuttle, for example. Or I think it was 6A when the ARM was brought up, where we had a hurdle failure, a common hardware failure that took out the entire CNC, command and data handling system, command and control of the whole space station. And there was a kernel of smarts that actually flew the station for part of the station while you were there, Shep, which we called Mighty Mouse, which basically stepped in. It didn't know there was a lab. It didn't know there was a truss. It didn't know there was anything else, but it knew enough about how to maintain enough connectivity to the ground that the ground could, follow the issue and so forth. So it's having some, should there be some standard that just requires we will have some very, very simple, very basic method for vehicle control that a human could understand, in that it is your backup chute, it is your last resort, and it's something that everybody trains into the task-based stick and rudder, wind in the wires level of intuitive ability to fly the vehicle long enough to get yourself well again.
Thanks. Shep, is your hand up, Neil, or is it left over?
No, just a quick comment on what Dan said. Another really valuable aspect of this dissimilarity is it allows you to basically unplug the main actor in the system and run it on some sort of different backup. And that's a great tool to figure out what's really busted. And I do that on my truck all the time. When I have something that's not working, I cut it out of the loop and see if I still have the problem. And if I do, I know it's something else. But this is again a kind of a work skill for astronauts. One thing I'd like to say about what Ali said, in terms of writing or understanding kind of where the code is going, it's kind of a dark hole, because you may want to be able to break out the signal analyzer and find that the bits going into the machine, there's something screwy with that, which could often be the source of why the computer is unhappy. So I agree, astronauts should have the ability to probe into critical things and figure out as much as they can on their own what's going on, but it can be a dark hole.
Okay, I think we've used our time wisely. I'd like to go around the table and just have ask each of our panel members to just say, if they were going to pick one topic for a bunch of smart people to work on to enable these kinds of semi-autonomous vehicles in the future, what would that topic be? We've all got a million of those topics, but what would be your favorite one right now? Make it very short. We'll just go around the table and then we'll wrap it up. Wex, you start.
I would hope that somebody is creating this operating framework where it's cohesive, the vision, the mission, the principles, the architecture, as Shep talked about, the reliability, and then the requirements, and then the testing, and then training. If it's written down cohesively, then everything else flows from that.
Thanks, Wex. Sandra?
I'm going to go with communication and interface, and I mean that bidirectionally too. Just getting what is the right information and how do we communicate between humans and the automation.
All right, and Aenor.
I feel the same way, that integration is probably the topic, whether it's across systems or time or components. I think that's key. And then I guess the other main thing is, if we're acquiring or sensing, that it's for a needs-driven purpose, so that we're creating some action out of it.
And Shep.
How do we increase the volume on these discussions and turn them into something that provides tangible results?
Excellent. Allie?
I'm going to have to go with human autonomy teaming. I can't claim that that's an unbiased comment, because that's what I'm most interested in, but I think it's critical. Otherwise it'll, it's at that interface where the failures will happen. And so I think that's critical.
Dan?
Yeah, I think mine is kind of along the lines of Allie's and Sandra's a little bit. I'd like us to get away from thinking about these as discrete things. The computer runs it, the human runs it. Maybe there's an intermediate hybrid case. It should be a continuation, and a continuum rather. and how to manage the situational awareness of the human so that they can upload themselves from various roles into flying the vehicle again, but do that through a blended, perpetually informed methodology.
Thank you, panel. I'm going to wrap it up with some thoughts about how to continue this conversation. After this panel last year, I think the panel felt like we had just scratched the surface. After this year, we just put a second scratch in the surface. There's so much more to talk about. And we have a silent majority of participants here that haven't said anything yet, but have a lot to say. If you have something to say about this, if you have comments, I put my email in the chat. I will collect them all. And then about a year from now, two things. We'll have this this panel again, maybe in person, I hope, Mr. Abbey. And we're also going to have a open workshop sponsored by the two NASA SmartHab Space Technology Research Institutes on paradigms for semi-autonomous deep space habitats. And we'll make sure that the word goes out through these channels, and you'll be welcome to attend that and get your inputs into this great big topic in a larger audience. So with that, thank you, panel members. Thank you, participants. Thank you for your thoughts and your patience. And I'll turn it back over to Mr. Abbey.
Thank you, Steve. Very good panel, and your points are well taken. And I hope you'll get some questions from the audience, and we can go forward with this and look at doing something better next year. Thank you all.